All right, welcome to this video. Today we are going to go over line balancing and working to takt time. So in this example, they need over the next week 500 units are required, and the working shift is 8 hours, and there are 5 days per week. So what is the takt time in minutes per part? Well, first let's discuss what takt time is. So takt, T-A-K-T, and in this case it's going to be minutes per part. So this can be equal to the time, and this could be in weeks, days, minutes, seconds, whatever is suitable for your scenario. But it is the time of a given period. And then that is over, in this case, it's going to be parts. But again, wherever you work, you may be measuring takt time differently. It doesn't always need to be a part. It could be an assembly. It could be a dollar value. But anyway, it's usually a quantity. Oh, quantity. Quantity required in the same given period. So in this case, our takt time is, our time unit is, 5 days per week times an 8-hour shift. So there's 8 hours per day times, and it says we want it in minutes. So there's 60 minutes in an hour. And that is all going to be over my required quantity. And in this case, I need 500 units. And just to keep the wording the same, we're going to say that there's 5,000 parts per week. So you'll notice a lot of these units cancel. So let's just cancel them out. So days cancel with days. We have hours canceling hours, and we have weeks canceling weeks. And so that's going to equal, let's pull up the calculator here, 8. What is it? I can't remember. It's 5 times 8 times 60. So 5 times 8 times 60. So that's 2,400 or 2,400 minutes within this allotted time or this given period. And that is over 5,000 parts. And so if we calculate this, we divide the 2,400 by 5,000. We're going to get 0.48 minutes per part. So we know that our system as a whole needs to produce a part at every 0.48 minutes. So in the situation here, this is what our production line looks like. So this is how the production line is currently set up. We don't know why, but it just is. And so if we look at the throughput times, we have 0.4 minutes per part for the shear. This one is also making a part every 4.4 minutes. The brake is making a part every 0.92 minutes. The assembly is making a part every 3 minutes, and the paint operation is making a part every 1.2 minutes. And if we staff each one of these stations with one worker, we end up with having 5 workers. So 1, 2, 3, 4, 5. So as always, I like to understand where the bottleneck is and that current throughput rate. So if we look at this assembly line, it's very easy to see that our bottleneck is here at assembly. And in the real life, these times aren't, shown anywhere physically. You would have to, measure that, and so you wouldn't really be able to see these times in real life when you're viewing the production taking place. But what you may see is that you have a lot of parts beginning to stack up in front of the assemblers. And you might see a lot of inventory between the shear and the brake. That is what you will see. That is the indicator that you have a bottleneck. And and likewise, you may have, since these workers can finish the part in 1.2 minutes and it takes 3 minutes, the paint is going to be starved. So what you might see is, workers standing around, not looking overly productive, which is not a good thing to, not really a nice position to put somebody in. So anyway, we want to, take a look at this and, change this for change this to our takt time. So the bottleneck appears to be in assembly. And the throughput rate, the current throughput rate is 3 minutes per part. So the manufacturing system is going to produce one part every 3 minutes because you're only as fast as your slowest process, which is the bottleneck at assembly. So this is much, much greater than where we need to be at 4.8 minutes, 0.48 minutes per part. Okay, and then likewise, where are there extra workers? Well, it seems to me that shear, has a relatively low throughput rate, just even one shear, and then there's 2 shear operations here. So what is, let's see if we can calculate this throughput rate, this throughput rate at shear. So there's probably extra workers at shear. And so, every 0.4 minutes, 2 parts will be made. So the throughput rate is equal to 0.2 minutes per part, which is way under our takt time of 0.48 minutes per part. So let's imagine that each station has capacity to expand or contract. So that means, and we want to balance the line according to takt time. So that means that we can, we have as many shears as we possibly need. We have as many breaks as we possibly need. We have as many workers as we possibly need. We have as many stations as we can possibly expand. Because this is, although this is an ideal situation, we're trying to calculate the ideal assembly line. You need to really kind of understand where you are right now and what the ideal state is, because you're not going to have enough breaks typically. You're always trying to allocate resources effectively, in which case you may not have enough breaks or enough assembly stations to meet your takt time. But you really need to understand where you are right now and the ideal situation to know, to have a good idea of what needs to expand to meet your takt time and what needs to contract to meet your takt time. So I've already done the math here to meet this, or I'm going to calculate this at this point. So I already have it drawn out, the amended production line, but I first want to calculate how many we need. So what I like to do is, look at each throughput rate. So, and compare it to the takt time. So at the shear station, I'm making a part every 0.2 minutes, or 0.2 minutes per part. As we stated earlier, that's way less than 0.48 minutes per part. So what I can do, obviously, is reduce this station to one shear operator. Okay, so we'll do that, and then this becomes with 0.4 minutes per part, which is under our takt time, which is good. We have a good process here, so that's good. All right, so now let's go to the next operation, which is break. So at the break station, I'm making a part every 0.92 minutes. So that's over or 0.48 minutes per part, which means that I need to maybe increase this. So I'll increase this by 2 stations, or one. I'll add a station. So every 0.92 minutes, I'm going to get 2 parts, which equals 0.46 minutes per part. And so that is less than our takt time. It's very close to our takt time, but still less of 0.48 minutes per part. So we are good here as well. Excellent. So assembly, we're making a part every 3 minutes. So in assembly, making for every 3 minutes we're making a part. And that is way, 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 way over our takt time of 0.48 minutes per part. So instead of just guessing how many stations I need, what I can do is calculate it. And how I do that is I divide my current my current throughput rate by my takt time. So it's 3 minutes per part over 0.48 minutes per part. And when I do that, I get 3 divided by 0.48. I get 6.25 stations. So in an ideal world, maybe you would have 7 stations and you have one person working a quarter of the day at the 7th station, assembly station. But I know I need at least 7 because it's over 6 stations, right? So I'm just gonna, for now, round up to 7 stations. So I can quickly do the math here to make sure that it works. So 3 minutes per 7 parts. And I'm going to get a throughput rate of 3 divided by 7. 0.43, we'll round up here to 0.43. So that's 0.43 minutes per part, which is under our 0.48 minutes per part, which is our takt time. So again, and it's very close, this worked out very nicely. So we are okay there. So now let's go into the final station, which is paint. And paint takes 1.2 minutes per part, and that is greater than ours, 0.048 minutes per part. So we'll calculate our station again using the same method. So we'll take the 1.2, we'll divide it by the 0.48, and let's see what we end up with. 1.2 divided by 0.48. We end up with 2.5 stations. 2.5 stations. Okay, so we'll round that up to 3 stations. Okay, so then we'll get every 1.2 minutes, we end up with 3 parts. So we end up with a throughput rate of 0.4 minutes per part. 0.4 minutes per part. Okay, so that is under our 0.48 minutes per part, and that is good. Okay, so now that everything is under it, let's redraw this assembly line again. Okay, and as before I said, I've already redrawn it here. So it's actually so big that it doesn't fit on here, so on my screen. So let me just change it up here. So I'll move these ones over, and I'll move these 3 down here, and then I'll move all of these sort of up, and we'll just understand that the brake goes to all of these assemblies, and then from these assemblies they go to paint. There aren't 2 different assembly stations. So just for the sake of making everything fit nicely on the screen, I'm going to just change up how this flow chart works. And we'll move all these up here. Okay. And I'll move this one here. Okay, thank you for bearing with me there. So we have our shear here, which is at 0.4. The brake is at 0.46, and the assembly is at 0.43, and the paint is at 0.4. So in an ideal world, we wanted all of the workers working at the same time for the same amount of time. This is how we would set it up. So what I want to know at this point is, are these workers, well, let's count, I want to know how many workers we have now. So let's count them up. So I have 1 at the shear, I have 2 at the brake, I have 7 at assembly, and 3 at the paint station. So I have 7 plus 3 is 10, 10 plus 2 is 12, 12 plus 1 is 13. So I have 13 workers. But I know that all of these times are under the takt time. So is maybe 1 worker or maybe 2 workers extra? We don't know at this point. We can speculate, but we have not calculated if we have an extra worker yet. And so let's calculate the utilization of each one of these stations or groups of stations to the takt time, with respect to the takt time. So to do that, I'm going to take these numbers up here and calculate the utilization. So I do 0.4 divided by the takt time. And that equals 83%. So these ones are worth these. So the shear operator is working at 83%, what they could be based on the throughput rate, and the brake operator or brake operators, there's 2 of them, are working at pretty good utilization here. So 0.46 divided by 0.48. So that's about 96%. And then the assemblers are working at 0.43 divided by 0.48, and that equals 90%. We'll round up to 90%. And then finally, the paint operators are working at 0.48, which is the same as the shear operator. which is 83%. So do I have an extra worker in here? And I would be able to know if the difference between 100 added up to 100%. So let's take a look at this. So 100% minus 83%. And so that equals 17%. So 17% of the time this person may be making more parts than are required, or the person is, depending on your manufacturing line, maybe you're doing full production, in which case they would be doing 17% other things not related to production. Okay, so then it might be as well possible that the operator takes more than 0.4 to stretch out the time. That's always a possibility. Okay, and then using the same math here on 100 minus 96, I get 4%. So they're working fairly close to takt time. Here they're working 10%, and again 17%, using the same math that I used over in these calculations. So again, this is for the shear break I guess this is assembly and paint. Okay, so I'm wondering if all this, sort of downtime that's not related to making parts adds up to 100%. So this is 21, 17 plus 4 is 21, 21 plus 10 is 31, and then 31 plus 17 is 48. So I see that, there's 48% of the time, not 48% of the time, I guess there's this amount of time not being used. And so this is less than 100%. So I guess the way to word this is no workers can be removed. So I know that in this situation, this setup here is the max efficiency I can get. Unless there are other things that you can do that I didn't talk about, and that is, maybe having different lengths of shifts. So maybe instead of hiring 3 painters, maybe you only have 2 painting stations in your company, in which case you need to have 2 painters during the day and then a painter at night, something like that. But you'd still have 3 employees altogether. So that gets a little bit challenging because it's more specific to your factory, what you can do. So maybe you don't have 2 breaks, you just have 1, and in which case you need to make a bunch of parts in WIP, to be processed over an evening shift. But then again, you need to make sure you have enough parts for the assemblers during the day. So there's a whole bunch of different ways you could split up your shifts. Maybe this might split up into 2 shifts very nicely to meet your goal, which is the 5,000 parts within the week. So there's lots of shift splitting that you can do to manage that, to manage your capacity of your machines that I didn't talk about in the math here. But that is how you can see if you are working very close to 100% productivity, is to do this utilization analysis. So anyway, that concludes the video on line balancing. and working to takt time. If you have any questions, leave them in the comments below. And I hope you found this video useful, and take care. We'll see you later.